is also not good because let's say, for example, for this round, I test that this piece of code is working for 1 second, the other piece of code is working for 2 seconds on this computer. Right? Then we noted it down. But then after that, we use these two pieces of code and run another machine, and it becomes like 0.5 seconds and 1 second, right? So we thought that it has improved, but actually it's the computer that has improved, right? So we shouldn't be using this. So we use what we call computational complexity. Okay. Computational complexity is a measurement of how efficient your code is supposed to be. Okay, so as the assumption is that your number of items grow big. So let's say, for example, you've always been testing on 20 items, but let's assume that the number of scores just now is not 20 students, but we stretch it to one whole cohort of students, which can comprise of 9-10 classes, each one having 30 students, which will give you 200-300 students or 400 students, and you spread it across. Let's say you have a nationwide exam. Okay, let's say for example the O levels, the A levels, the PSLE. Then you'll be spreading out to 30,000 students, something like that. Okay, so how do you make your program efficient for, let's say, 30,000 students? Okay, so we use computational complexity to measure that. Okay, it's about how many instructions that the computer will actually execute. Okay, assuming that n grows large. Okay, assuming that n grows large, we will find out how efficient the program works. Okay, so we can reduce the runtime by increasing the performance. Okay, or decreasing the complexity. Okay, of course, if you do increase the performance, you install a program in better, faster computers, you can do that, but you are still not solving the problem of having what we call poor algorithms. Okay, so you should have good algorithms, and if you can do good algorithms and then decrease the complexity, you can actually design the program better and then therefore faster. Okay, so to quantify complexity, we need to measure runtime growth, how many instructions will be executed, okay, and how many instructions will be executed, and of course, relative to the size of the input, how many instructions will be executed. Let's say for 10,000 items, will there be 10,000 executions? Or can I reduce the 10,000 items? If I have 10,000 items, can I reduce it to, let's say, 20 executions? And if, let's say, you increase your 10,000 items to 100,000 items, will I have 100,000 operations, or can I just increase the 20 operations to 40 operations? So is it possible? Okay, if you can grow your n very large, but the number of instructions do not grow large, that means you have an efficient algorithm. Okay. However, let's say now I have 10 items, I run 100 instructions. I have 20 items, I run 400 instructions. That will be very poor algorithm. Okay, that will be a very poor algorithm. To measure this type of algorithms, we use what we call a big O notation. Okay, this is one of the simplest math you can actually get. Okay, if you know how to use it, is probably one of the simplest. Okay, big O notation measures for a problem of size n the complexity of a program. So it can come in the term of what we call O1, which is constant time. The runtime does not change with the input size. So even you have one item, 1,000 items, 1 million items, you will only run that few instructions. Okay, so it doesn't really change. The second one is to have a linear time. As n increases, the runtime will increase together with n. So like I said, if you have one simple example is that you have one item, you run one time. You have 10 items, you run 10 times. You have 100 items, you run 100 times. So this is what we call linear time. Okay. The quadratic time is very bad. Let's say, for example, you have one item, you run 10 times. 10 instructions, you have 2 items you run, no, sorry, you have you have one item you run one time, but you have 2 items you run four instructions, right? So that's like square like that. So if you have 3 items, you run 9 instructions. Okay, so it will increase in the terms of square. That's why it's called quadratic, right? So that's not very efficient. Okay, so far okay, right? Okay, quite simple. Huh? Okay. Okay, so if you look at this thing over here, this will try to take in a list of items, but it will always print the first item. And the first item is always at position 0. So you will execute one instruction. Okay. For 10 items, I don't care whether it's 1 item, 100 items, 1,000 items, you will only execute one instruction because you are printing always the first item. Yes, Jackie. 15 or 20%, I can't remember. Answer your question already, yeah? 15 or 20%. Yeah. Maybe for you, you find it easy or difficult? Okay. Oh, okay, then no problem. Okay, this is what we call O1. This is called O1 complexity, right? So whether you have 10 items, 100 items, 1,000 items, the number of instructions run is actually flat. You can think of this as time also. The time is actually flat. Okay, time is actually flat. Okay. Okay, example 2. Example 2, you have this function that runs in linear time. Okay, when you have a list of items, you want to print all the items in the list, you are looping through the items, right? So for 1 item, I print 1. For 2 items, I need to loop 2 times to print 2. 10 items, I need to loop 10 times to print 10. So this is what we call a linear time. So very easy to see. If you have a for loop, it is ON. Okay, if you have for loop, is ON. Okay, for loop is ON. Right, so this is how it works. So 0, no instructions, 20 items, 20 instructions, 100 items, 100 instructions. This is ON. Simple, right? Okay. Okay, third, we have what we call quadratic time. You have a for loop within a for loop. So this is what we call ON square. Okay. This is running, let's say you have 10 items, you run from item 1 to item 10. This one will run from item 1 to item 10 for every item. Okay. So for every item, you run an inner loop, which will execute. Let's say you have 10 items. For every item, you run 10 times inner loop. So for 10 items, you run the inner loop 10 times. So it's 10 times 10, 100 items. Okay. Right. So for 100 elements, you execute 100 times 100, which is 10,000 times. So this is n squared. So if you plot the graph, it looks like this. Okay. As the input size increases, the time goes up, okay, more steeply. So if you compare all of them, the best will be O1 complexity versus ON complexity versus ON square complexity. Right? But of course, these are not the only ones. Later on, I don't know whether I said it in the exam, whether you have O log n or not. There's a O log n. There's a O n log n. Okay. And other complexities like n cube exponential. Okay. So we'll take a look at that. Okay. Big O notation is another way to think of it is that it's an expression for how many instructions will be executed as a function of the size n, okay, discarding all items except for the fastest growing one and discarding coefficients. Okay, so to make things very simple, if I have computed that the algorithm will run 3n squared plus n times log n plus 1000 times n instructions, I will just take the biggest power and then discard everything. And this is my complexity. Right? It just throw away everything. Okay? I just throw away everything. Okay? Why is it the case is because, let's say I have, I think it will be clearer. Let's say if I just do this, okay, let's say plus 10n plus 50, okay? Let's say, for example, let's say I computed it to be this, okay? And then if I say when n equals to 1, the number of operations equals to 1 plus 10 plus 50, that's like 61, right? Okay. When n equals to 10, that will be 100 plus 100 plus 50. Number equals to 250, right? But when n equals to 1000, it will be 1000 times 1000 plus 10,000 plus 50. I think too much zero, right? So it's like that, okay? So let's do it one more. N equals to 100,000. So your num will be 100,000. Well, I also don't know how many zeros. How many zeros? 1, 2, 3, 4, 5. 5 plus 5. 1, 2, 3, 4, 5. Okay. Then after that will be 100,000 times 10. That will give us 1,000,000. So I put the comma first. Okay, like that. Right? Then the last one is 50. Right? So this is almost equivalent to 100,000 times 100,000. Almost equivalent to that, which is 10 million. So it means that as n goes big, the coefficients and the smaller powers are actually negligible. That's why you only take the biggest one. Right, so that's the reason for doing OM. But of course, it's not very accurate. You realize that if I have a 3 in front, it's actually quite significant. If I put a 3 in front, it's actually 30 million. 30, is it 30 million? It's not 30 billion. 30 billion executions. Okay, it's actually quite significant. Okay, but for simplicity's sake, we will just take ON square. Okay, so no questions. I'm going to move on. Denise, Jackie, anyone? No, Ho Chin, sorry. Jin Lee.
What if that equation has 2n squared?
If you have 2n square plus n square, that's just n.
What I mean is n to the power of 2 plus maybe another n to the power of 2.
That's just simply n to the power of 2, the biggest one.
The biggest one?
Yes, I don't care about the rest. Yeah, so I don't care about the rest. It's just the biggest one. So if you see, let's say n square plus n square plus n square plus n square is simply n square. Okay. Large question with 3 marks. No, it's not a large question. It's a question that you need to explain with, I think, 2 or 3 marks each. Yeah. Okay, so computational complexity, okay, can. Okay, so for this example here, this is O1. One single loop, nothing inside. Make sure there's nothing else inside. Okay, nothing else inside except for printing the item. If you put a function inside, that's a different thing. Okay, because a function will mean something else. So this is printing the item only. This is ON. For two loops, they are almost the same in size or the same in size, then it's called ON square. Okay, also do not be tricked. Later on, I'll show you some examples. What do I mean by do not be tricked? Okay, so okay, constants do not matter in big O notation. If you have O2 is equivalent to O1. If you have O2n plus 1, you take the biggest one, throw away the constant, throw away the coefficient, it's simply ON. Okay, it's very simple. That's why I say big O notation is actually very simple. It's just that you need to show the intermediate working. That's it. Okay. Okay, if you look at this, the first function prints the first item. The second function prints the first item and the last item. This one gives you one execution. This one gives you two executions, right? So whether you have 1,000 items, this one will print one time. This one have 1,000 items. This one also print two statements. Okay, so the growth rate is the same. So their complexity is simply O1. Okay, so don't be fooled by the number of statements. Okay, so complexity, whether it's 1, 2, they are taken as O1. Okay, whether they're 1 or 2, they are taken as O1. Right, similarly for this, this is a list of items. Right, so let's say this is n, you are printing n times. This is n, you're printing n over 2 times because you're taking half the list. Okay, so therefore, whether it's n or half n is still ON. Okay, makes things simple for you, right? Okay, complexity you can see the same. Okay, it's the same. Okay, so I think the next example is also the same. Right. So only the most significant terms actually matter. Whether it's ON plus 1, just take the biggest one. ON square, take ON square. N square plus 1 times n. Okay, this is important, is n cubed. So n cubed is the one. Throw away n. Okay, always take the biggest one. Okay, so let's take a look at one example over here. Okay, you have a matrix, and this is a number. So he's looping in for every line in the matrix, and for every item in the line, you print the item. Forget the rest. Print the item divided by number. Right? So you have one inner for loop, one outer for loop. I don't even have to calculate this. I know it's ON square. Right? So how do we show the working? Okay, question is how do we show the working? Right? So let's say, for example, you want to show the working. This is one execution. This is considered n executions. This is considered n because you're looping through n times. Okay. But the execution is actually here. So this one is n times as well. Right? N times. Okay, and this one will be, sorry, this one will be n times within n times. And this is belonging to the outer for loop. So this one is n times. Right. So for this is actually n times, right? Yep. Okay, this is actually n times. This is definitely 1 only. Okay. This is looping in n times within n times. So this one is n times n, executing n times n. This is n times. This is not exactly executing. This is only looping. So this one we can throw away. The actual execution is the one with the print statement, print statement, print statement. Okay. So this is looping n times n times. And this one is the outer 4. So that's why you have 1 plus n square plus n. 1 plus n square plus n. I did not do this. I just use this line by line, and then I will get O n square because of this working over here.
So the print is because of the item and the number that's n squared.
Yeah, the print is the which one? Which one?
For the print item divided by a number. Because of the two factors, so it's n squared.
Because of the two, for the two for loops.
Yeah.
Yeah, because of the two for loops. Any questions? Jackie, especially, since you asked a lot for this one. No. No question. Not yet. Okay. Right. So whether you have n square or n1 plus n square plus n, it will give you the same complexity. So in big O notation, always consider the worst case scenario. So depending on the input data, runtime can actually vary. Okay. So we are always considering the worst case scenario. But in the course, it didn't let you know that the big O notation is not always accurate. Okay. If you want to really compare between two algorithms, this is what we call a rough comparison. Okay. If you really want to compare which one is the better one, then you have to take in terms of the coefficients as well. Okay, but it's not necessarily this case as well. Okay. Okay, let's see. Another example over here. If number is greater than length, number equals to length. For index in range of 0 to number, print list of items index. So, okay, let's say, for example, you have a list of items which is 100 items, but you put in 10. That means you only print the first 10 items. That's what I'm saying. Okay. If 10 is greater than 100, no, right? So for index in range of 0 to 10, you're trying to print 10 items. Okay. If let's say I key in 1000 and your list of items have only 100, so you will take the length. That means you can only print all the items inside the list. So you print 100 times. Okay. So this part here, what it's saying is that you will always take worst case scenario. Okay, always take a worst case scenario. Because a good case is when your number is 0, then this will be executed. The rest are no longer executed, right? In a case whereby you have 1000 for your number, but your list of items is only 100, then your number will be 100. And that's the worst case scenario. Okay. So you will need to execute this and then execute this. So this is considered 1, and this is n executions. So therefore it's 1 plus n O n. So you take the worst case scenario. All right, no problem. I think Jackie also no problem. No questions yet. All right. Complexity is not always obvious to measure because this one looks like one line, but then again, it is not one line. Okay. Looks like one line, right? So if I use this, this is 1, this is actually O1. But then that's wrong because summing of the items is actually a loop. Okay, so inside the function is actually on because you're looping through the list of items to add all of them up. Okay, so in this case, the big O notation is actually on. All right, any questions? All right, no issues, right? Okay. Yep, and that's about it for the slides. Any questions at all? If not, then I will go through a few examples with you on the big O notation. No? So quiet? Waiting for... Okay, no question. Need example. Yeah, quite a lot of examples already. Okay, now we will run through the example. This one. Okay. Let me see how to close this. Okay, so this one is on lecture 9. Okay, so big O. Here we come. Okay, so simple one will be using loops. Say, for example, okay, I'm going to use a main. And then I want to do, never mind. I'm lazy. Give me a moment. Okay, I'm going to use this as an example. So number of items. Okay, so what I'm going to do is I'm lazy to generate this. So what I'm going to do is I'm going to use for I in range of number of items. Okay, I'm going to get a random number equals to random dot ran from low to high, and then I'm going to append this to the numbers, and then I'm going to return the numbers. Okay, see whether you understand this. This is a blank list. I'm going to generate a random number. Add to the list. Okay, so here I'll put in my numbers equals to generate random number Okay, what do you think this is trying to do? What do you think is the ON of this? Quite simple, quite simple, right? So what's the ON of generate random list? Forget about the numbers. The numbers are not important, right? Okay. So what do you think is the ON of this? What is the big O notation of generate random list? Anybody can tell? ON square? How come ON square? Okay, ON, right? So let's try. Okay, this is one execution. This is only one execution. This will be n executions because you're running this in the loop n times, right? Your number of items, you're running n times, okay? Appending is just putting the random number to the back of the list. So it's just actually also n times, okay? This append is a simple adding to the back. So it's not a very complex, it's not a very complex operation. But of course, there are some things that's going behind, but normally it's just a simple operation of one. Okay, normally, okay. This generation is also a simple operation of one. So, but it's inside the loop. So n. So all in all, the total is O. The O is actually O1 plus n, and that will give us O n.
I saw it differently.
Okay. I saw it differently. I thought it's ON square.
No, I said ON because I based it on definition made. So I treated 3 to 9, 3 to 10 as just a function, but the main function is definitely. So I thought it was ON from that.
Oh no, it's the ON of this function. Yeah. Okay. So Jackie got it? You think so, huh? Okay. So what I'm going to do here is I'm going to count. Okay, I'm going to add in one more function. Okay, this is a bit long. Okay, so we have the numbers, and then we have a lower bound, and then a higher bound. Okay. So let's say we have a count equals to 0. So for the least, if number is smaller than lower bound, count equals to count plus 1. Okay, let's say after that, oh sorry, count out of range numbers. So that is a low count. And this one is the high count. Okay. Okay. Without knowing what is trying to do, okay, return the count of numbers below the lower bound and the count numbers above the higher bound from a list of numbers. Right, so if let's say I have a list of numbers, I want to count I want to find out how many numbers that are below 10, how many numbers are below 80. So this one will return us two counts. One is the number below 10 and the other one is the number of below above, let's say 80. ON square. Okay, the algo itself is not exactly that important in this case because we are looking at the ON. Okay, so think about how to count this. Actually, not difficult.
Plus the top. Plus the proof.
No, the define is not counted. The everything here, even return also not, you can don't count. You count the statements from here to here. Even if you count the last one, is okay lah. But I mean, just count from here to here. Or you want to include the return is fine. You don't include it, that's also fine. Negligible. Okay, so how you say ON square? Still ON? The answer is still ON. Okay, the answer is still ON. Because this is 1. This is 1. This is N. Right, so this is one loop. This loop has nothing to do with this loop. So this is another N. Arguably, if you enter this, this is 1. So the calculation is O 1 plus 1 plus N plus N plus 1. And that will give us O N plus 2N plus 3. And that will give us O N. One loop is n. Only you have inner loops, then it's considered O(n) square, whichever. Okay? One loop only. The loops are on the same level. So that's why it's O(n). We will do two more examples, not just one example. Yeah, we'll do two more examples. Okay with that? Okay, so I can actually make use of this. This is actually a working program. Let me just get num lows and num highs equals to count out of range numbers, lower passing in my numbers, and then I want to count below 20 and above 80. Okay, so let's print this for fun. This one just print for fun. Okay, this is not needed for the big O, but it's just for fun to see that it's working. Okay. Okay, this is just for fun. Okay, let's just run it. Okay, you have one whole long list of what? Just nice 12 and 12. Sure or not? Wait. I want to be sure first. Numbers. Okay, look different already. Okay. Correct. Then 5 and 12. Okay. So it's running. That's a coincidence. Okay, just a coincidence. Okay, so it's working. So it's working. This one is just to show you I'm running two different algos. One is to generate a random number, right? Set of random numbers. And the other is count numbers below 20, count numbers above 80. You have this or not? This comma. You haven't. Quite good. What ON? Yeah, these two, there's only two. I never do extra example. Not yet, not yet. This one is just for fun only. Jackie, this one is just for fun. This one is not I haven't created a third function. Depends on what you key in here. It says 50 numbers. So how do you get 12 and 40? I'm not sure. Having errors. Okay, you want to share your screen then? Enabled already. Because you put in too many brackets, line 32, you go and put double bracket. Should be one bracket only. Yeah. Jeffrey, you want to check? You check for your own first. You still cannot walk over to you. Jeffrey, how? You want to see? What is the error? What's the error? Take a look at the parameters first line. Okay, I go all the way up. Low and high. Oh. Yes, it's random. Of course, the numbers are different. It's random, but for him, he gets 12 and 40, which is weird unless you go and put in this as more than 50. So what do you put here? You put 50, then how can it be 12 and 40? Or your comparisons are actually wrong. Scrolling down, all down. Three parameters.
There's a new issue now.
What's the issue?
Number you type only name error number is
Okay, guys, ready? Share screen. Okay, can. Waiting for you to share screen. Jeff. Okay, wait, you put 51, 20, 80, num lows, num high. Apparently your calculation is wrong. If you see 27, 27 line 27, you go and put smaller than, it should be greater than. Okay, run. Sure, 331. Okay. You can manually count if you want, but should be correct. Right? Okay. All right. Anything else? Can run already, right?
Yeah.
Okay. So I'm going to okay, I think let me see. Okay, so I'm going to go with another example. I'm not going to use the same example, otherwise it will be too complicated. So here I'll create another example. Okay, for two last examples. Okay, two last examples. So this one will be big O again. Examples 2. So big O examples 2. I'm just creating another file. So the first one we will run through, of course, is the matrix, right? So it's the matrix. So we want to create, let's say, a random matrix. Okay, let's import the random again. Okay, we put in the main, we put in the pass, we put in the main. Okay, standard code now. Okay, standard code for now. Okay, and then we want to generate. Okay, we want to do matrix equals to generate matrix. Okay, so currently it's not working because we don't have the method yet. Okay. Okay, so let's say, for example, we want to generate the rows equals to 4, columns equals to 3, and then our low equals to 1, or 1, and high equals to 30. Okay, so we could think of it as rows, columns, low, high. So we're going to generate, so this one has to generate a matrix with 4 rows, 3 columns, and then random numbers from 1 to 30. Simple, right? You understand? Okay. Okay, so we're going to generate the matrix over here. Define, generate matrix. Okay, again, I put in four arguments, means that I need 4 arguments over here. Okay, I need 4 arguments over here. Okay, I can name them the same. Okay, maybe I'll name them a bit different so you can tell the difference. Okay, so I put this as num rows. I put this as num columns. And I put this as low bound, and then put this as okay. I just name them differently so that you do not mistake that I have to name them the same. Okay, so this one I can put rows, columns, low, high. Okay, so generate rows by columns matrix with integers from low to high. Right, simple as that. And then we will do for row in rows. No, for row in range of rows. So this one is looping through the rows, okay. For column in range of columns, so that's looping through all the columns for each row. Okay, for each row, we do a pass first, all right? Okay, so this one will tell you that if I have 4 rows, I need to run this 4 times. Okay, if I have 4 rows, my inner loop has to run 4 times. Right? So if I have 10 rows, my inner loop has to run 10 times. Okay, and depending on how many columns I have to run that. So if in this case, 4 rows, each column run, each inner loop run 10 times, so a total of 4 times 3, 12 times. Right? 4 times 3, 12 times, right? Okay, so for each time we will generate, okay, a random number. So this random number is the same. We can take from the previous one anyway. Okay, so this one will generate a random number. Okay, the question is how to put this into the rows and columns. Okay, that's a big question. Okay, that's actually a big question. Okay, we could append, but the thing is, when we append, I think all of you were confused. Okay, so I'm not going to do that. Okay, so what I'll do is, first of all, oh yeah, we can append. Okay, let's just do a simple matrix. Okay, so this is an empty matrix. Okay, so this one will be a matrix row. This one will be a matrix row. Huh? Okay. Every row, we will append the random number. Right? So after this loop, the matrix row is filled with columns items, right? So number of columns items. Okay. And then we append the matrix row. So we append the row to the matrix. And finally, we return the matrix. Okay, so see if you can understand this. But I think the ON And the big O notation is quite simple to understand. So what's the big O notation of this? Quite simple, right? Yes, after a few tries, you got it right. ON square. So eventually, with determination, you get ON square correct. Just kidding, okay? Okay, yeah, it's ON square. Okay, so I'm going to count, okay, I'm going to count each of them. Huh? So this one will be 1, right? This is 1. This is inside the row. So this is actually, I'm going to put it to the next line so that it's not confusing. Okay. So this is 1. So this will be n because it's inside the for loop. Okay. So this part here is n times n. This part here is n times n. And this part here is n. Okay, let me move all these here so that it's on the same column so you can see properly. And this one here is a simple 1. Okay, so the code will give you O1 plus n square plus n square plus n plus 1. Wow, very nice. This one is binomial theorem. Something like binomial theorem. Okay, almost. So this one O2n square plus 2n plus 2, and that will give us ON square. Right, so if the loops are on the same level, then it's simply a ON. But if the loops are not in the same level, it's actually indented, then this will be ON square. I think the exam paper probably needs you to show the working. Yes, you can get the marks for the right answer, but working, you need to score.
Working, you mean the bottom left, right?
Yeah, this one. You can count. You can do this. Yeah.
So we're not required to type all that thing out, right?
Which one?
The matrix, the
So the 1 n square n 1. Yeah, then come with the last line.
Okay.
Yeah, you not everything else. At least for the cheat sheet, you know that you can get some marks. Okay.
Sorry, so all the tables, right?
This part not counted. Only the one that's executed.
Yeah, so for let's say row 9, there is n, right?
Yes.
Do we need to put that into the exam?
Like that. Yeah. This one is.
We need to do the entire list and then go, right?
Yeah. Then after that, do the working.
So
Identifying the statements to execute. Right? Not difficult. Actually, not difficult. It takes a bit of practice. Okay, guys, are you all okay? Okay, all right, Jackie, Ken, just one quick last example. I think an additional 3 to 5 minutes only. Okay. Okay. So, Jackie, this next example is not O n square. Just kidding. Okay. This example here. Okay, this example here is not inside your notes. Okay, but it gives you an idea. Okay. So it's this one is the big O examples 3. Okay, it will be very, very simple code. Okay, very simple code. I'll give you 2 loops and you can see. Okay, I give you 2 loops. I'm not going to put them in any functions. Okay, so let's say for example, I have a total equals to 0, and for I in range of say 100, right? I want to say total equals to total plus 1, no, total plus I, and then I try to do prints. The total is equals to total. Okay, so this one 4950. Okay, this is an obvious ON, right? This is an obvious ON. This is 1, this is N, and this is 1. So total, actually O 1 plus N plus 1 equals to O N plus 2 equals to O N. Okay, this is a simple, obvious ON. All right? So no questions on that, right? Yes. Okay. So now let's take a look at another one. Okay, let's take a look at another one. Okay. So if you print this, if you print this, okay, if you actually print this, okay, this one is just for showing only, showing only. So actually print this one will print n times. Okay. So if I actually run 100 times. Okay, so I keep it to 5. So this one will print 5 times, right? 1, 2, 3, 4, 5, right? Okay, so this one will print 5 times, right? So if I, of course, this is 100, then this thing will print 100 times. Okay, I'm not going to count, but you know it's 100, right? You know it's 100. Okay, so this will print 100 times. Okay, so why is it important? Okay, let's take a look at another loop. Okay, the last loop they're going to see. I have another total. Okay, another total. I'm going to call it total 2 equals to 0, or maybe I call it something else. Don't call it total. Total count equals to 0. Okay, and then for I in range of okay, no, I'm not using this anymore. Number hundred while number is greater than 0, total count equals to total count plus number, right? Number equals to number divided by 2. Okay, so this part can remove the brackets. That should do the trick. Okay, so total is 197 because I divide by 2 every time. Right. Question. you got the answer already. O log n. Okay, O log n. Why? Because your 100 divided by 2 becomes 50. 50 divided by 2 becomes 25. 25 divided by 2 becomes 12. 12 divided by 2 becomes 6. Becomes 3, becomes 1, becomes 0. Right? So you did not execute 2 to the power of, wait, let me see, 2 to the power of 4, 2 to the power of 5 is 32, 2 to the power of 6, 2 to the power of 7. So this one will run either 6 or 7 times. Okay, let's try that. Okay, let's try. This one will run either 6 or 7 times. Okay, so this one should print 7 times. 1, 2, 3, 4, 5, 6, 7. Because it is O log n. You try 100 log base 2, you will get 7. Less than 7. Okay. So this is this type, when you do a division, this is log n. How to explain? Cannot explain. You cannot count. You simply cannot count. Okay. You can only say that this is there's no working for this in this case. So this one is O log n. Okay. If you really want to explain, as the total is always divided, as the number of executions equals to log base 2 of 100.
So when log base something, then it's gonna be log n.
Yeah, you see divide by 2 every time is log n.
So if it's divided by 3, then it's not log 3. I mean, it's still log n.
Divide by 3, that one still considered log n. Still considered log n. Okay, any questions? But no, usually no log 3, not divided by 3 one. Usually it's divided by 2 because it's computers. Why? You spread. You next time when you do, if you ever study binary search, you'll know it. Okay. Any questions? If not, thank you. It's already past 10 p.m. So is Jackie, you got it correct already. You got 2 out of 4 correct. Congratulations. Okay, I got nothing else for you. So right, so before you go, you can check the portal for assignment from tomorrow onwards. If I forget to accidentally turn it on, just give me a beep. You know my email, right? This one is my email. Okay, I think which email did they give you? Don't know. Is it this one? Or is it another one? Did they give you any email? No email. Kaplan email. Cannot be, right? Don't use this one.